Hello and welcome to lesson 4. Last lesson, we looked at the mole as being equal to the Avogadro's number of particles, meaning 1 mole of atoms is 6.02 by 10 to the power of 23 atoms. So 1 mole of carbon atoms is 6.02 by 10 to the power of 23. The mass of 1 mole of carbon atoms can be found by going to the relative atomic mass of carbon in the periodic table, and you'll see it's 12.01 grams. But what about something like chlorine, a molecule which you would find its relative atomic mass in the periodic table as 35.5, but what is the mass of 1 mole of chlorine gas? Well, what you need to do is to go into the periodic table, see 35.5 for 1 chlorine atom, multiply that relative atomic mass by 2 to get the relative molecular mass of the Cl2 molecule, and that comes to 71. And the relative molecular mass of chlorine would be given as 71 grams, making up 1 mole of Cl2 gas. That Cl2 gas would be made up of 2 multiplied by 6 by 10 to the power of 23 moles of chlorine atoms. But with gases, there's another way to know how many moles you've got, and that is with these 2 bits of information. 1 mole of any gas, whether it's chlorine, whether it's methane, whether it's oxygen, whether it's nitrogen, ammonia, any gas at standard ambient temperature and pressure, room temperature and pressure, but the proper notation is to say standard ambient temperature and pressure. The ambient environment, the surroundings, the SATP conditions are 298 Kelvin, and you get that by adding 273 to 25 Celsius. 298 Kelvin, 1 atmosphere of pressure. At sea level, we have 1 atmosphere of pressure. So under those conditions, 1 mole of any gas occupies 24.0 decimeters cube, dm cube. 1 dm cube equals 1 liter. So you could think of a 1 liter bottle filled with carbon dioxide, and you have that bottle at 25 degrees Celsius and at sea level with 1 atmosphere of pressure. Then inside of that 1 liter bottle, you would have 1/24th of a mole, because 1 mole is 24 dm cube, which is 24 liters. You would have 1/24th of a mole, and then you could find out how many carbon dioxide molecules you have by finding 1/24th of this. If you wanted to find the same information under standard conditions, then you could. And under standard conditions, 1 mole of any gas occupies 22.7 cubic decimeters or 22.7 liters. We should also know that 1,000 cubic centimeters, 1,000 cm cube makes up 1 dm cube, and 1 dm cube makes up 1 liter. So 1,000 cm cube makes up 1 dm cube. 1 dm cube is equal to 1 liter. So 1 mole of carbon dioxide gas at SATP occupies 24 dm cube, 24 liters. 44 grams makes 1 mole of CO2. So 44 grams of dry ice. If we were to acquire that and we allowed it to undergo sublimation, which is to go from the solid state directly into a gas, we would get 24 liters. We would be able to fill 24 1 liter bottles with CO2 with just 44 grams of dry ice. But how many atoms would you find in 1 mole of carbon dioxide? So if you had 24 dm cube of carbon dioxide gas at SATP, you know that you've got 1 mole. But if I then asked you how many atoms do you have in that 1 mole, you'll have to bear in mind that a mole of CO2 is made up of a mole of carbon dioxide molecules, and each carbon dioxide molecule is made up of 3 atoms. So you then have to multiply 3 by the Avogadro's number. And then that would give you 18.06 by 10 to the power of 23. But you should not leave your answer as this. You should be able to convert it into scientific notation or to standard form, where you're not allowed to have 18. This number here has got to be somewhere between 1 greater than 1 and less than 10. So you've got to make this into 1.8 by shifting your decimal point back this way. And to compensate for that, you've got to change this 23 into a 24. So you've shifted your decimal point over to the left, and then you add 1 to this 23, making it a 24. So you will get this as the number of atoms in 1 mole of carbon dioxide molecules.